This is a series circuit with a known resistance and an unknown impedance named X. We're asked to calculate the voltage triangle and power triangle. We're also asked to calculate the series current in the circuit and work out the value of the unknown impedance named X, along with the total circuit impedance. The supply voltage Vs is 160 volts AC. We're told that the real or true power is 500 watts and the power factor is 0.88 lagging. The lagging power factor means that the impedance of component X must be inductive overall, but what we don't know is whether component X is an inductor with a second resistor as shown here, or just an inductor on its own. So here's the voltage triangle of a circuit with a lagging power factor. It shows the supply voltage Vs, the imaginary voltage which is across the inductor, and the real voltage which is across the total resistance. From trigonometry, the hypotenuse is the adjacent side divided by the cosine of the phase angle phi. The adjacent side is the cosine of the phase angle, which is the power factor, multiplied by the hypotenuse. Then we can use Pythagoras to find the opposite side of the triangle, the inductor voltage or imaginary voltage. The triangle is the same shape with the same phase angle whether it's the voltage, power or impedance triangle. They are all mathematically similar. Step 1. Calculate and draw the voltage triangle. The cosine of the phase angle is equal to the power factor. So the voltage across all resistances is equal to the supply voltage multiplied by the cosine of the phase angle. So the voltage across all resistances is equal to Vs times the power factor. So the real voltage is 160 multiplied by 0.88, which equals 140.8 volts. We can use Pythagoras to find the inductor or imaginary voltage, which is the square root of Vs squared minus V real squared. The inductor voltage is 75.996 volts, call it 76 volts. So that's the voltage triangle completed. We could have found the phase angle, then used it to find V real and V imaginary using cos and sine, whichever way works for you. Step 2. Calculate and draw the power triangle. We know the true power P is equal to the apparent power multiplied by the cosine of the phase angle. P therefore equals S multiplied by the power factor. So apparent power is true power divided by the power factor, which gives S equals 568.1818 volt amps. We use Pythagoras to calculate reactive power Q, which equals 269.8714 volt amps reactive. Step 3. Calculate the series current. So true or real power equals the real voltage across all resistance multiplied by the current. So current is real power divided by the real voltage, and this comes out as 3.55 amps. So the total resistance from Ohm's law is the real voltage divided by the current. This comes out as 39.662 ohms, and this proves that there's an additional resistor within the component X, as the total resistance is more than 20 ohms. The hidden resistance is the total resistance minus the 20 ohms, so subtraction shows us that the hidden resistance that I call XR equals 19.662 ohms. The inductive reactance within component X from Ohm's law is equal to the inductor voltage divided by the current. This comes out as 21.407 ohms of inductive reactance. Combining real and imaginary will give us the complex impedance of component X in rectangular form. Adding on the 20 ohm resistor gives us the total circuit impedance of 39.662 plus the 21.407 j ohms of inductive reactance. Step 5. Choose a frequency and an inductor value, then simulate on multisim. We know that inductive reactance is 2 pi times the frequency times the inductor value in Henry, so the inductor value L is the reactance divided by 2 pi f. I've chosen 50 Hz, so the inductor value needed for this reactance is then 68.1406 millihenry. Here's the multi-sim results, and it gives peak-to-peak values, so these are twice as big as our calculated peak values. So our current is therefore correct, our imaginary or inductor voltage is correct, and the real or resistor voltage is correct. So we did everything right. We identified our unknown component and worked everything out. I hope this was useful, and thanks very much for watching.